Hello all. So I'm going to talk about transfer operator approach to quantum wave function. We are going to do this in a relativistic setting. That's why, mostly, that's why I put relativistic in the title. Actually, I turn my camera on so that you can, in fact, see me. All right. So let's start with this. I'm pretty sure everybody at this workshop is familiar with the Koopman operator theory, but let me just speak a little bit because I want to set up a bit of history. We all know that Koopman reformulated dynamical systems theory in terms of evolution of observables. He did this inspired by quantum mechanics. Originally, it was really done to study measure preserving systems in classical mechanics. So it was done in phase space. In the last 20 years, we've done quite a bit of dissipative system analysis, and the theory was ported to obtain data-driven methodologies, data-driven in the sense that dynamical systems object can be surmised from data, and the geometry can really be explored using the operator theoretic methods. The key idea is that the spectral objects associated with the operator can help us understand the state space geometry, even produce objects such as modes that are projections of observable vectors to eigenfunctions. Recently, it has been extended to control. I don't know if anybody has seen, but there is a book on Koopman operator in systems, methods in systems and controls that Alex Mauroy and Yoshihiko Suzuki and myself have edited. I should mention here at the beginning just the relationship to stochastic process theory. You can view today's dissipative analysis as essentially non-stationary stochastic process theory for a certain class of processes. But in this talk, that's how much I'm going to say about the kind of standard applications of Koopman operator theory. And here are the pictures. I know Peter Morgan sent a younger one of Koopman. Here is the one that is standard. And then von Neumann and him extended it pretty soon, very quickly to deploy ergodic theory. What I'm going to talk about today is a little bit of a return to the roots. When as I studied a variety of applications of Koopman operator theory and their extensions, I was wondering why the two of them didn't actually go back and try to understand how to apply this to quantum mechanics itself. It's such a natural idea because, of course, one has operator theoretic developments both in quantum mechanics and in classical dynamics. And it's natural to try to connect the two. And I may actually go through this slide. A number of us did. I will apologize. I'm sure this is not a complete list. I'm sure there is somebody at the workshop that has also done work in this Koopman to classical to Koopman quantum. I immediately see that Frank Wilczek's little PDF that is online on his website is actually not stated here, but here is some partial list of applications in non-relativistic, where mostly it's done through the phase space and Wigner functions. And then the one that I know that is relativistic is by Dimitri Giannakis. I don't know if Dimitri is on the call. By the way, can you see my cursor?
Yes.
Okay. I don't know if Dimitri is on the call, but his paper is interesting and shows aspects of what I'm going to tell you about here as well. So let's just recall the standard Koopman setting. We have observables on phase space M. They go from M to C. The Koopman operator is a composition operator, discrete time, mapping T here. Continuous time, we have a flow. ST, again, a composition operator. The original papers are Koopman's in PNAS, and then Karleman, who did Karleman linearization, who I think got told at some point that Koopman did something similar, and then Koopman and von Neumann in 1932 applied it to figure out systems with continuous spectrum. By the way, they clearly knew that chaotic dynamical systems can have chaotic behavior. It's really instructive to read some of these original papers because that was 30 years before. before Lorentz. They stated very clearly that you can have dynamical systems with continuous spectrum that have, probability distributions that are absolutely continuous with respect to state space, phase space measure. So in the vector field case, we have x dot is equal to f x, and the generator equation over here. I'll move the picture of everybody in the call, and then we have the adjoint, the propagation of complex densities, and I'm going to work with that today. And then the eigenfunction equation is clearly on the operator evolution side. In measure preserving case, this is unitary, so it's usually labeled as u. Ut phi is e to the lambda t phi. And for the generator f, the vector field f dot grad phi is lambda phi. A nice example is that Hamiltonian is an eigenfunction of the Koopman operator at eigenvalue 0. This almost immediately points out to us that we can do some physics with the operator. And so let's try and do. Here is my setting. I'm going to work on a 4-dimensional space-time, pseudo-Riemannian manifold endowed with a metric tensor G. Tm is going to denote the tangent bundle. V is going to be the 4-velocity field. X of tau, where tau is proper time, is a time-like world line parameterized by the proper time. The norm, the pseudo-Riemannian manifold norm of the vector field itself is minus c squared. So I'm clearly using minus 1, 1, 1, 1 metric convention. So minus 1 for time. G tau, I'm going to denote the flow of V on M. In the classical case, I denoted by ST, going to be G tau, so parameterized by proper time. D tau F is going to denote the proper time derivative, the Lie derivative of F, which is, as we know, a covariant quantity. And then that's going to represent the change of scalar physical quantity in direction of V. And then square root of determinant of G is the volume form density. So that's my notation. Okay, so here is the connection to Koopman. The flow on the pseudo-Riemannian on space-time can be used to define the family of Koopman composition operators parameterized by tau, acting on functions, or what they in classical relativity would call invariance. By u tau f is f composed with g tau. You will see that there's going to be an underlying Koopman operator as I go. But there is a little bit more in this formulation that I'm going to discuss. I should mention that as many of the papers that I mentioned before deal with Koopman's formulation of phase space, this operator doesn't act on phase space. It acts on functions defined on the spacetime. And so the tau is the generator of the evolution that is equivalent to this here, the generator of evolution. But the generator itself is d tau, the Lie derivative of functions on spacetime. So if I have this equation here, d tau f is equal to 0, just like Hamiltonian was conserved in the classical case, f here is conserved on the world line based on this. So this is the meaning, the physical meaning of this equation for any function f. If I find a function f that satisfies this, it's conserved on the world line. In terms of the Koopman evolution, u tau f is f. So the composition operator would propagate basically a constant along trajectories. Okay, any questions so far on the setting? No. All right. Now we're going to consider a real density just to set some intuition. I'm going to consider real densities on the real line. And suppose that I have a density, and then I would like to understand the distribution of observations. So mu of h under observation h, given the density rho. So in terms of measures, mu is the density of the push forward. So you're looking at the density on the real line, and you're observing it through some observable h. So integral mu of h dh, that's how much stuff is in A, is integral over h inverse of A, right? rho of x, that's the measure, that's the density that is the real density. You're just observing it through h. And then clearly I can replace dx by dh divided by dh over dx. So in other words, mu of h is rho over dh dx. If this reminds you of statistical mechanics and the fact that if you restrict to energy surfaces, you get an expression for the conserved volume on the energy surface, something like this, then that's a good sort of intuition. If I have a complex h, so this is my key point, on multidimensional real rho, we get mu of h is rho divided by the spatial derivative of x, and this now, in non-covariant language or non-manifold language would be, of course, the gradient in Euclidean space, where dx stands for spatial derivative. So the intuition here is if I have rho, and if this is very, very big, if the gradient is very big, then I'm going to see very little when I view it through function h. So the function h could be very steep. If this is very small, then I'm going to be, if this is very flat, then I'm going to be seeing the real thing. So that's the intuition. And so here is what I'd like to postulate here. Unfortunately, I cannot see my titles, but so here are the postulates that I'm going to use. I'm going to say that there is a field y that I'm observing the density rho by. That's the idea. Oops. So I'm going to say that there is rho. There is a field y. These are the key objects, and here is a trajectory. And I'm going to say I'm observing rho, whose meaning is going to become clear with dimensional analysis in a second. But bear with me for now. I'm observing rho through a complex field. So the way I can visualize this is that every point of the trajectory, I look at a circle around it. And instead of rho, I have rho over ik e to the minus iy. So this is precisely the same as what I've shown you here, except that I have e to the iy as the observable. So I have a complex scalar field that I'm observing the density with. That's the mathematical assumption. I just want to see what I can do with my dynamical system that I have defined with this particular assumption. And so I'm going to say the following. I'm going to say the lead derivative of rho is 0. So rho is some density whose meaning I'm going to examine soon, that is actually conserved on trajectories. And then next, I'm going to call this the observable wave function is the push forward of rho by e to the iy. So you can clearly see that e to the iy, if I put it up, is sorry, this should be a minus, is a phase, and then k here is 1 over dy, norm of dy. All right, so rho, my true density, is being viewed through e to the iy, and this is the equation that ensues. And here is what you can prove. So let's set y is equal minus s over h. So clearly, I'm now saying the phase in the e to the iy that I'm observing is essentially the action in the negative divided by the reduced Planck constant. And then the lead derivative of s is L, and L is the standard Lagrangian. So the wave function psi, the way I've defined it, I'll make a connection to standard notions, is IH d tau psi is minus L psi minus IH, divergence of V psi, where the divergence of my 4 velocity is is given here in coordinates. It's the standard, and it's the standard expression. And for those of you that have worked in curved in Dirac theory in curved space, I should reflect almost immediately that this object shows up. So if you read, for example, original Fock paper on this, somewhat surprisingly, divergence comes in. And if you have worked in this space, then you know that this is a non-hermitian, that you end up with non-hermitian aspects of the theory that you have to modulate by changing the density. But this equation is zero spin, clearly. It's manifestly covariant because I have Lie derivative here, and I have invariance on the other side. So it's a relativistic equation. And so let's see the proof. The proof is simple. I had this expression here. So I just differentiate that and multiply by IH bar. I get 2 terms instead of 3. And I have rho, k, and y to deal with. D tau rho is 0, so I have 2 expressions to deal with. If I differentiate e to the minus iy, d tau y shows up. If I differentiate k, 1 over k, this shows up. And then I have to deal with both terms. D tau y is my Lagrangian, so that shows. I should point out that, of course, y is minus s over h, so minus Lagrangian comes in. D tau k over k is this term. Here I'll have to deal with that. So I have my part of my theorem. So here is the Lagrangian. I'll have to deal with this part. So remember, k is the norm of dy. So I need to find d tau dy, and I claim this is the norm of dy, the divergence of v. How is it? Well, rho over dy, crucially, is a density, the way I defined it. It's the original density divided by a gradient, norm of the gradient of a function. So it's a density. So Liouville theorem tells me that the Lie derivative of a density, well, Liouville theorem on curved space tells me that the Lie derivative of density is minus the density itself times the divergence. This divergence is with respect to square root of determinant of G. But also I can directly differentiate this to obtain that. If you compare this and that, you're going to come with d tau dy is dy dv. I plug that, which is d tau k, into here, and then we obtain that equation. So this is the equation I came up with, that at least if you accept the physical aspects of this, tells you something about the evolution of a density. So let me interpret the density. Before I do that, let me say something about the operator theoretic nature of this. Clearly, I have the generator involved, so that's d tau, that's the Lie derivative. And I also have a field involved, observation field. So it should be more than just the Koopman operator, and indeed is. One can easily show that the solution of the previous equation is at any point y in space-time and any proper time tau, I get composition of psi 0 g minus tau y. That's the Koopman part. I just look back and look at what my function was at the initial point. But then there is this integral here. So first of all, there is the integral of divergence of the forward velocity along the trajectory in space-time. And then there is e to the is. This looks very much like Feynman, but integral. I don't know if Bedros Afayan is there, but he pointed out a couple of years ago to me that there should be a close connection, and so in fact it is. And then you can represent this as psi 0 of x0, that integral and that integral. So what is the operator? So the operator is actually what is called a weighted composition operator. So you compose a function with a flow, And this is more in the Perron-Frobenius sense than the Koopman, because it's density. So it's you're composing it with the negative evolution. And then you multiply by pi. This is the weight that depends on your final point. So here it is pictorially, and this is clearly, similar to what you would do in the path integration formulation of the theories. All right. So let's do a little bit of dimensional analysis just to see. So far, this was mathematics. I assumed existence of a certain velocity field. I also assumed that I'm watching it through a complex scalar field, which, by the way, if one accepts that physical reality, that tells me immediately why I square root of -1 appears in such a problem. So it's immediate because the field that I have postulated exists is actually a field that is basically a cylinder around every trajectory that you're observing trajectories through. So that's the ontology. But here is something interesting. If psi is rho over dy in the modulus, the probability density, and here is the key. Remember, rho is the density, so psi, modulus of psi is the density as well. So the probability density from the classical quantum mechanics, Schrödinger's, Born's quantum mechanics, must be norm of psi divided by the integral of norm of psi d mu, and that has to have dimensions of 1 over LD. If I'm going to integrate this over any dimensional configuration space, it must be 1 over LD, which means that this guy here is non-dimensional. Well, if it's non-dimensional, then rho, this is non-dimensional, that's non-dimensional. So then rho must have units of spatial wave number, because dy is phase divided by something, by some spatial scale, and therefore has units over 1L. So that's interesting, because my density actually is a density of, rather, if the wave number is larger, so if there is more oscillations, then rho is bigger, and if there is less oscillations, then rho is smaller. So the physical meaning of rho, which is going to become important in a second, seems to be that is the density of oscillations at a point. And so, okay, let's take that line of thinking a little further. One can think of trajectories as carrying waves propagating in time with certain frequency, where rho is nu over c, right? So the frequency nu would be rho times c, and then m is equal to rho h bar divided by c, has dimensions of mass. So this is to indicate that space-time trajectories oscillating higher frequencies have higher mass. And then, indeed, if you know some vibrations, higher frequency of oscillation indicates higher stiffness, leading to the idea that mass reflects the stiffness of the underlying trajectory. What I'm pointing out is, and this part is obviously at this point interpretation, is that if I set this up as my rho that I came out of, a axiom, a sort of postulate type form, if I set this as m, then I have kind of a physical understanding of the underlying trajectory in terms of some vibrations. All right, so I'm going to show that this is actually entirely in line with the concept of mass in string theory, as you might have already thought for a second, because I'm talking about the stiffness and therefore some tension should be. And here are some references that on string theory that I'm going to reference here. So here is a slide on resonance and matter in this context. So consider the case of action that is relativistic. So mc squared tau. So the frequency of the vibration of S of my field, which remember is just y times minus y times h, is mc squared over h bar. That's the frequency. Now remember what I just said, that I have another frequency, and that's the frequency of oscillation along a trajectory, that is rho times c. So let's talk about resonance and set this up equal to that. So you get mc squared over h bar is rho c. In the case of resonance, omega s over omega is rho c h bar over mc squared, which implies precisely what I talked about a second ago in a speculative form. So this relationship arises precisely from saying that your observation field is oscillating at the same frequency as the underlying wave. Well, if we want to extend this, this implies that observation of a matter object of mass m, provided there is a resonance between the internal trajectory of oscillation of a string and the frequency of oscillation. I may push this a little further. So let's read a little bit on string theory. So here are open strings in space-time, and here are closed strings. The rotating string, like something like this, would start from here and then spin around. And here is its impression of oscillating along a trajectory that it's following. So the resonance condition, if I replace m with mu 0 ls, c squared is rho h bar c. And then if you let T0 be the string tension, from standard string theory, you're going to get this. If you replace, so T0 is the tension, sigma 1 is the parameter at the end of the string. Sigma 1 T0 is rho hc, T0 is rho c h bar over sigma 1. I'm not going to go long through this, but if you now use our assessment that rho is just 1 over the length, you get T0 is h bar c over sigma 1 ls, and you actually get precisely out. So this is the part that comes from what I've discussed before and the physical interpretation. You get exactly the tension that as it would exist in string theory. One thing that is physically interesting here is that this mc squared term does not come from any property or nature of the underlying vibration. It's really the oscillation in the observation field. How much more time do I have? Anyone? Okay, I'll just proceed and then see when I'm. Okay, so let's go through some examples. Let's say that we have 1 + 1 flat space. So in any dimension, let's set up in the standard way that the gradient of y is just velocity multiplied by m divided by h bar. And then let's take the norm of that. And we're going to get that v is equal to c over j, where j is c over v. That's over here, that's clear. But that's the index of refraction. So it's kind of interesting that it comes up. Recall the mass relationship that I just derived. M is equal to rho h bar over c. Rho is the density that I've used in deriving that equation. And then we get that the norm of dyx is rho over j. That's nice because it actually tells you something. It tells you that rho over j is what would in usual context be a square of the amplitude that is appearing in the classical wave function. And so for the wave function, we have this expression here, but now j, you see, is c over v. So that's where if c is large compared to v, we are going to get some interesting results. So let's use the same assumption. Rho is conserved along trajectories. F, the observation field, is e to the iy. D tau y is the Lagrangian. Well, Lagrangian tilde, because really y is minus s over h. I obtain this equation that has a wave, one-dimensional wave part, a divergence part, and a Lagrangian part. And more compactly, you can write down something that looks like a Hamiltonian, and that Hamiltonian has a part here that has to do with advection and Lagrangian. and then the divergence term that, as I pointed out, shows up also in Dirac. And if you look at some recent papers on Dirac and curved space, you're going to see 1/2 here. And the reason for that is that psi is the modulus of it is the square of the size that are used in those papers. In d dimensions, the equation looks something like this. Here is the solution that I described previously, but here is the interesting part. If you look at that part with L here, so if you look at this part here, so that's V, and minus AH partial with respect to X is P. So it's really a quantization of this H here. And it clearly shows that P, that is actually the property of the oscillating field, and V, that is the velocity, are separate quantities to deal with. I had an interesting discussion with Dennis on that where he observed it. Dennis Bondar on that, where he observed it as well. Let me say a couple of more things about examples, but I won't go through them in gory detail. One can write the wave packets. Does anything new come out? Yes. So what you get from the equation is that the wave packet width is suppressed. So interestingly, when you go to relativistic speeds, sigma squared, which is your initial spread of the wave packet, for gamma, if you accelerate, in this case, spins 0 particles, you would actually go back to original spread. This was actually observed in intense laser fields using the Dirac equation. There's some experimental evidence for this. How does this look like in space-time? It is the harmonic oscillator in space-time. With a little bit of work using the periodicity of trajectories, you can solve. This is basically the equation that I gave you before, which psi of 0 is the Koopman part, and this is the part multiplying it. For that integral to be periodic, you use this condition. You can come up, you can integrate that, come up with a condition for lambda, the eigenvalue. So I'm solving the eigenvalue problem of that equation. And long story short, if you use m is rho h bar divided by c, you get exactly lambda is omega h n plus 1/2. I should point out that the 0-point energy here occurs very naturally because of the oscillations of the observation field. So they're not the property of the dynamics. They're not associated with any pilot wave. It's the property of the oscillation of the observation field. And by the way, that nature of the spectrum that I just derived, where omega n times h bar is just the Koopman part, and this part here is associated with the multiplication part, that's typical of weighted composition operators that I've just described.
I guess I think I have a few questions, but maybe we can talk also offline. One question I had about this, the variable, the field psi of, which is a function of position and proper time, right? I know that in the slides that appeared in equation 17, if that's of any.
You want me to show them?
Sure.
Yep.
So, oh, thanks.
This.
So is that evolution? Maybe I might have missed that. Is that compatible with the flow on the space-time manifold? Namely, if I take the field and I apply it to the point that I reach after evolution by proper time tau, starting from tau, is it the same as and evaluating at tau equals 0? Is it the same as evaluating the field at the point y and proper time tau? I'm not sure if my question was very clear, but
okay. So no, I think it's clear, and there is a little bit of a setup that is in the paper, but it's not in the slides. So one does have to take a slice, synchronize, right? So take a slice of space-time manifold for the events that have the same proper tau. But this can be done locally, right? And then extended by the flow. So in some sense, you have to synchronize the proper time clock, right, on the space-time manifold. So it's a good question. It's resolvable.
Okay.
Of course, at least locally, right? So if you want to work globally, of course, you extend it to the point where you can. Thanks for that question. That actually does address a technical part. Does that answer your question? Because I think the question was essentially, well, everybody has their own proper time. So how do you exactly make sure that you can actually look back, right? And the way you do this is just imagine a two-dimensional space-time slice, right? And take the proper time evolving. Just take a slice of constant proper time, right, for everybody, and that's what's embedded in the solution here. Yeah. So I should point out, of course, this is actually an important question. This is not a single trajectory theory, right? So it does deal with the evolution of the space-time manifold, and maybe I'll say just one last thing. The point here is there is one single field. This whole problem of quantum mechanics being such that it's defined on the state space actually goes away here. You have one single field that's defined everywhere on space-time. And if you want to understand how particles act, that problem is just like doing vortices in fluid dynamics, right? So you have a stream function that is defined everywhere. But if you want to know how point vortices interact, you're going to go to a state space description. So the ontological problem that, for example, bomb theory has, or anything else, completely goes away if you assume the field here and the underlying velocity. So
any other questions?
Yes, I have a question.
sure.
Is there an underlying assumption that perhaps you were not explicit about, that the space-time on which you are working has a time-like killing field?
That's an excellent question as well. I actually did start with that. Interestingly, at the end, I don't think I needed it, right? So for example, the divergence-free condition and kind of nice things that come with killing fields, not necessarily, but I didn't get to go through the curved, to the Dirac equation on curved space. And in that particular case, of course, the original derivation of the equation is using parallel transport. And so you need the Vierbein, right? You need the four-leg kind of construction. So that's what you need. And if you utilize whatever function you can utilize to actually get to that, that's enough. But thanks for that question. Yes. Does that clarify?
Well, more or less, because I think there is the question that lingers in my mind is how unique is that choice, for instance, the Vierbein or whatever you want to do. Right? Even in flat space-time, we have, the boost killing fields that we could use as time-like killing fields, and then we have, the standard Unruh effect and things like that would appear in quantum field theory and so forth. So I'm wondering how unique is the construction.
Again, I'm very glad you asked this. So let me point out how I think about it, and you will see that I think that it's quite consistent with what you've just said. So if one looks at Takebayashi and type of hydrodynamic theories, one assumes there is a velocity, velocity, right, on the space-time manifold to start with. And so the idea here is that what you're observing through this observation field, of course, you can account for in the context of matter, but everything flows. And that's the underlying assumption. So if everything flows, there is clearly everywhere a somewhat unique construction. So let me qualify that. Certainly there is a vector field V, the four velocity that is there. And that has the norm, of course, minus C. But if you start with that, then you can define the normal, the binormal, and a trinormal. And that gives you something that's very similar to Fermi-Walker type transport. So apart from, so that's unique, right? So apart from that, I don't really see any.
It's unique if you have a single velocity field, but I can imagine in a realistic situation, for example, having photons flowing in one way, and for some odd reason, neutrinos of certain flavor flowing in some other way, and then you having many velocity fields at your disposal. And the question is whether making different choices.
Yep. So this is I'm a little bit sad I didn't get through the last part of the talk, because it got increasingly increasingly more interesting in this direction. Indeed. So just like you have many fields in principle in field theory, you could have different velocity fields that are described in the manifold, and that would be a natural extension of what I've talked about. What is interesting to me is that if you look at, maybe I'll share just for a second and talk about Dirac for a second. If you look at how the Dirac equation can be constructed, instead of my density rho, you say, okay, I'm going to have the density rho times L, which is some wave vector, which is some vector in the rest frame, times lambda, which is Lorentz transformation to lab frame. And you get back the Dirac equation. This is in 2 times 2 special matrix formalism. So you get this back, and you get the evolution equation for that particular field, right, with that particular velocity. Now, you could have a separate field for, let's say, photons or neutrinos. What stays the same, it seems, and I will boldly mention this, is that the quantization always goes by saying first d rho is equal to 0. So conservation in this particular case of the vector, and this is the wavelength vector. So rho now is a vector. The square root of it is the classical Dirac spinor, but the rho itself is a vector. I know Landau called it 1/2 vector, but it's really a square. Spinors are really square root vectors, right?
Mm-hmm.
And then what you do to get this wave function, observable wave function that I have defined, is you divide by norm of dy. So the quantization procedure itself, so I should say, because it's probably become obvious, that what I'm talking about is really a quantization procedure, where you have something conserved on the trajectories, and then you divide by dy. Now, I thought about photons and even gravitons. It's interesting that in order to get spin 1 or spin 2, you do have to start increasing the dimension of the space, right? But this part, the quantization itself, I think stays the same. And so indeed, you can have many different fields. What I meant by a unique field really is this observation field that stays the same. Does that describe it better? Thank you. Thanks for that question.
Thank you.
That allowed me to go into the last part of the talk, although not in any detail.